Welcome back. Let's now discuss a little more about the receiver. As you recall, in the block diagram of the receiver that I showed previously, we had not only the mixer, but I also had a pre-select filter. What I'm going to discuss now is the need for this pre-select filter. Now, you recall that from what I said before, that we have to adjust the LO frequency with respect to the RF frequency so that the absolute value of the difference between them is equal to the IF frequency, being the IF frequency, the frequency that we want this signal at the output of the receiver stage. Now, since once we fix the local oscillator frequency, it turns out that there are two possible, if we don't have this pre-select filter, there would be two different RF frequencies that would satisfy this condition, right? Because this baseband filter is fixed, this LO frequency is fixed, and therefore we would have two different RF frequencies that would satisfy this condition. This is graphically shown in this diagram. Right? We have the LO, we have the IF, and therefore we have two possible bands of RF frequency that can go through the system if we don't have this pre-select filter. Right? Now, as we have seen before, one of these bands, the lower band, will have spectral inversion, and the upper band will not have spectral inversion. The mission of the pre-select filter is to select only one of these bands because only one of them will have our desired signal, right? So we want to prevent noise and stray signals from getting into the receiver through the band that we are not using. And that's the reason why we have to use this pre-select filter. Now, the pre-select filter will have a certain frequency response like this and might have some insertion loss in the passband, right? This pre-select filter may be placed either ahead or behind the low noise amplifier. In principle, if everything is matched, the frequency response of the receiver is not affected by that. However, there are other considerations that will determine if we want to place the pre-select filter ahead or behind the low noise amplifier. And actually, this consideration is a compromise between noise performance and robustness to interference. If we have an environment in which the interference is strong, we can expect to have interfering signals getting to the input of our receivers, then we want this pre-select filter to be ahead of the LNA because these interfering signals can drive the low noise amplifier and generate nonlinear effects and other non-desired effects on this low noise amplifier and all the other elements behind that, right? So if we are in an in an environment with interferences, we want this pre-select filter ahead of the low noise amplifier. However, as I said, this low noise amplifier has insertion loss, and this insertion loss acts as an attenuator ahead of the amplifier. And as you know, attenuators ahead of the low noise amplifier of a receiver have a strong effect in degrading the overall noise performance of the receiver. And this is something we don't want to happen. So if we place this pre-select filter ahead of the low noise amplifier, it's very important that we minimize the insertion loss in order to not degrade the noise performance of the receiver. Otherwise, if we don't expect the environment to be, if we don't expect interfering signals in our receivers, we also have the option of placing the pre-select filter behind the low noise amplifier. Going in more detail about what I've just said, I put a slide here where I make a simplification on the behavior of the low noise amplifier and the filter. Here I'm only considering the insertion loss in the passband of the filter, and what I do is remind about the equation relating to noise involved in this case. You recall that when we place an attenuator ahead of the amplifier, we have to take into account the equivalent noise temperature of the attenuator. Generally, the equation that gives the equivalent noise temperature of an attenuator is this one, in which T is the physical temperature of the attenuator and L are the losses of the attenuator. For example, if the attenuator dissipates half of the power going through it, L would be 2, right? If it dissipates, if only 1/10 of the signal going in translates to the output, then L would be 10, right? So in this convention, L is greater than 1, right? So this equation gives the equivalent noise temperature of an attenuator, and if we calculate the overall equivalent noise temperature, then we have that the overall equivalent noise temperature would be the equivalent noise temperature of the first element, which would be the attenuator, plus the equivalent noise temperature of the low noise amplifier, but referred to this point, which is, and to refer this to the input, we would have to multiply this equivalent noise temperature of the amplifier by L, right? And this is the resulting equation that gives the equivalent noise temperature of the attenuator plus LNA. And for the case that I've shown before, this attenuator is placed here to take into account the insertion loss of the preselect filter in the passband, right? So the conclusion for this is that the insertion loss for this filter in the passband has a very detrimental effect on the overall noise performance of the receiver, because in one hand, the equivalent noise temperature of our receiver will be multiplied by this insertion loss, and on the other hand, we are adding this additional term, right? So when we place a filter ahead of the low noise amplifier, we have to be very aware that the insertion loss of the passband in the passband of the filter will degrade the noise performance of our receiver. So these filters have to be designed very, very carefully. And this concludes this section of the lecture on fundamentals of transmitters and receivers.